Hello everyone, in this lesson I will talk about the TCP/IP networking model. The Transmission Control Protocol and the Internet Protocol family were developed by the Department of Defense both to ensure data integrity and to protect and maintain communications in the event of a war, so a TCP/IP network can be truly reliable and flexible if designed and implemented correctly. Now let's look at the history leading up to TCP/IP. Networks today use the TCP/IP networking model, but previously there were not many network protocols, including TCP/IP. Manufacturers created their own network protocols, and these protocols worked only on computers they manufactured. For example, in the 1970s and 1980s, the computer company with the largest market share in the market was IBM. IBM released its System Network Architecture network model in 1974. Other vendors created their own private network models, and if you bought computers from all three companies, you could communicate by creating three different networks and then connecting those networks together. In the late 1970s, the Open System Interconnection, or OSI reference model, was created by the International Organization for Standardization, or ISO, to remove this limitation. The OSI model was developed for the interoperability of networks of different manufacturers. The OSI model is a primary architectural model for networks. OSI describes how to transfer data and network information from one application on one computer to an application on another computer through the network environment. Here's how each manufacturer used its own network protocol in the 1980s. IBM computers would create a network between themselves, other manufacturers would create a network between themselves, and then you could use it by networking between all three manufacturers. By the 1990s, TCP/IP was slowly becoming more and more widespread. Devices using IBM were again creating a network among themselves, and other manufacturers were creating a network among themselves, and then we connected these networks using TCP/IP. By the 2000s, all manufacturers started to use TCP/IP and our devices started to communicate over TCP/IP. On this page, let's give an overview of the TCP/IP networking model. The TCP/IP model is a broad protocol model that allows computers to communicate, and RFC documents are used to define these protocols. Another institution is the IEEE, which specifies the IEEE Ethernet standards, and the RFC determines the protocols. Let's look at the TCP/IP and DoD model. The DoD model is basically a condensed version of the OSI model, consisting of 4 layers instead of 7. Process application layer, host-to-host layer, internet layer, network access layer. Here he shows the comparison of the DoD model and the OSI model. In the DoD model, the first layer is the network access layer, the second layer is the internet, the third layer is host-to-host, and the fourth layer is the process application layer. Here the first layer of DoD corresponds to the first and second layer of OSI, where the second layer of the DoD model corresponds to the third layer of the OSI model, where the third layer of the DoD model corresponds to the fourth layer of the OSI. Many protocol series come together in the process application layer of the DoD model to define the various activities and tasks described by the top 3 layers of OSI. The process application layer defines node-to-node application communication and controls user interface arrangements. The host-to-host layer is parallel to the transport layer of OSI, dealing with issues such as creating secure end-to-end communication and error-free transmission of data. The internet layer corresponds to the network layer of OSI, defines protocols related to the logical transmission of packets throughout the entire network, deals with the IP addressing of user machines, and functions such as routing packets across multiple networks are performed at this layer. The network access layer, on the other hand, monitors the information circulating between the user's machine and the network, corresponding to the data link layer and physical layer in the OSI model. The network access layer controls hardware addressing and defines protocols for the physical transmission of data. On this page, let's talk about the application layer in TCP/IP, layer 5, where users actually communicate with the computer. This layer is activated only when there needs to be access to the network in a short period of time. TCP/IP, it's like a network interface card. You can remove all of the network card components from the system, but you can still use a web browser to browse local HTML pages. But if you try to do things like browse an HTML page that needs to be searched using HTTP or download a file via FTP or TFTP, the web browser will try to access the application layer and respond to such requests. The application layer is also responsible for identifying appropriate communication partners and determining whether sufficient resources are available, tasks that are important because sometimes applications require more than just desktop resources. Examples include file transfers and email, which will require remote access, network management activities, and client-server operations. When we look at the figure here, we can see how the HTTP protocol mechanism works. Here user Bob opens the web server and sends the web page request to the web server here. On this server Bob returns this page to the user. So how do these processes take place? The web browser here HTTP header also transmits the address of the page at once here with the HTTP GET request message. The server here says OK to the HTTP header and transmits the desired page to the Bob user here. After transmitting the page he wants, Bob transmits the data in this page to the user here, and simply the working mechanism of the HTTP protocol works in this way. Let's talk about TCP/IP transport layer on this page. The services in the transport layer divide the data from the application layer, reassemble it and combine it into the same data stream, provide end-to-end data transfer services, and establish a logical connection between the sender and the destination in a network community. The TCP and UDP protocols operate at the transport layer, while TCP's reliable UDP is an unreliable service, so application developers need to choose between two protocols when working with TC/IP, either they will use TCP or they will use UDP. The transport tier is responsible for providing mechanisms for multiplexing top-tier applications, creating sessions, and shutting down virtual circuits. It also provides transparent data traffic and hides the details of the information about the network from the top layer. You can see examples of TCP and UDP port in the figure here. The port number of the FTP application is 21 and it uses the TCP protocol. The TFTP application uses port 69 and the UDP protocol. DNS, on the other hand, uses port 53 and can use both TCP and UDP. This is our transport layer, and this is our application layer. All of the applications we use here have a port number, and these port numbers use either TCP or UDP. On this page, let's give you an example to better understand TCP and UDP, and we can give you an example of a phone call to help you understand how TCP works. We know that before we start talking to someone on the phone, we first need to establish a connection with the other person, which is similar to a virtual circuit set up with the TCP protocol. If you give someone important information during your call, you can say, "Do you know?" or "Do you understand it or not?" Saying such things is similar to many TCP confirmation packets designed to verify you. Sometimes people also ask if you are still there, and at the end of the interviews, they finish the call saying goodbye. TCP/IP performs exactly the same functions. Using UDP is similar to sending a postcard. To do this we do not need to establish a connection with the other party first, simply write our message, specify the address to which the postcard will go, and we mail it. This is similar to the connectionless orientation of UDP. We do not need a confirmation from the sender of the message on the postcard as it is not a matter of life or death, so it does not require UDP confirmation packets. In the figure here, the user in the web browser first sends TCP/SAN packets to the web server returns TCP/SAN packets to him, and then in the third stage, the web user sends the confirmation message, that is, ACK packets, and performs the TCP connection with the three-way handshake, that is, the three-way handshake. On this page, let's talk about TCP/IP network layer, Layer 3, also known as network layer. Layer 3 manages device addressing, tracks the location of devices in between, and determines the best way to move data. That is, the network layer is responsible for transferring traffic between devices that are not locally connected to each other. Routers are Layer 3 devices and operate at the network layer and manage routing services in a network community. First, when it receives a packet from the router interface, it checks the destination IP address and checks to see if there is a route for that address in the routing table, and if there is a route in the routing table for that address, it frames that packet and sends it to the egress interface. If there is no record in the routing table for the destination address to which the packet will go, the router cancels the packet. Two packet types are used at the network layer. The first is data packets and the second is route update packets. Data packets are packets used to transfer user data across a network community. The protocols used to support data traffic are specified as routed protocols. Examples of routed protocols are IP version 4 and IP version 6. Route update packets are used to update network information on neighboring routers connected to all routers in the network community. Protocols that send route update packets are referred to as routing protocols, with commonly used routing protocols being RIP, RIPv2, EIGRP, and OSPF. Route update packets are used to help create and maintain routing tables on each router. The figure here shows a simple example of IP routing, where the LARA user's IP address is 1111 and the destination address is 2222, so Bob will send a packet. Here, this user sends the IP header to the router checks the destination IP address here. If there is one in the route table, it sends the packet to the router 2 from that output interface, and the router 2 forwards the packet to the user, and in this way, a simple routing process is provided. On this page, let's look at the data link layer and its physical layer with TCPIP. The data link layer provides the physical transfer of data, but also handles functions such as error reporting, network topology, and flow control. The data link layer uses the network hardware address and is responsible for converting messages from the network layer into bits for the physical layer. At the data link layer, users use their MAC addresses at the data link layer to send packets to other devices on the local network and transfer packets between these routers. Finally, when we come to the lowest layer, the physical layer has two tasks, sending and receiving bits. The bits come and go only in a numerical Morse code at the value of 1 and 0. When we look at the figure here, in the first step, Larry creates the Ethernet frame by encapsulating the IP packet between an Ethernet header and the trailer. In the second step, Larry physically transmits these Ethernet frame bits using the electricity flowing through the Ethernet cables, and in the third step, the router physically receives an electrical signal through a cable and tries to reconstruct the same bits by interpreting the meanings of the electrical signals. In the fourth step, router 1 separates the IP packet from the Ethernet frame by discarding the Ethernet header and tray, so that the data is transmitted at the data link layer and the physical layer. Let's talk about data encapsulation on this page. As you can understand in what we have explained about how all layers perform their functions, we can express it as a data encapsulation process to the process of adding its own header information to the data provided by each layer top layer when sending data. In TCP/IP, sending data to hosts is a 5-step process. The first 4 steps are related to the encapsulation performed by the TCP/IP layer. The last step is the physical transmission of the data by the host. As you see here in the first step, the application data is created and encapsulated with the required application layer titles. For example, the HTTP OK message can be returned in an HTTP header and then in part of the content of a web page, while in the second step, the data provided by the application layer is encapsulated in a transport header, usually using a TCP or UDP header for end-user applications. When we go to the third step, the IP header is added to the information coming from the transport layer in the network layer, and after the IP header is added, the Ethernet header is added to the beginning of the packets from layer 3, 4, and layer 5, and the data link layer and the trailer is added to the end, and finally the first layer, i.e. the physical layer, is transmitted to the opposite device with electrical signals. We call this data encapsulation. That's all we have to say in this lesson, so goodbye to see you in our next lesson.